Okay. So we're at lecture 19, and as is customary, before we get into the meat of the topic, today's news story, not exactly newsworthy to most of the world, but I thought it was relevant to some questions that came up when we talked about MapReduce and warehouse scale computers. So this is, just today, an announcement for the release of a new tool. So when we were talking about MapReduce, a couple questions came up in terms of, how do you figure out what processing gets run on which machines? What happens when the output of one MapReduce job needs to get fed into another MapReduce job, and so on? And my answer at the time was that a lot of that stuff is kind of hand configured, right? And this announcement today from a company called Cloudera, which is one of the companies that supports Hadoop as their business model. It's an open source company. Just released a new system, also open source, called Crunch. And what Crunch does is, it takes a high-level description of what you want to do, and then compiles that down into multiple Hadoop jobs, and then manages the processing and execution of those multiple jobs. So as stuff's coming out of one reducer, it's getting fed back into another set of MapReduce operations. So the reason I show you this isn't so much because I think you're going to immediately download this and use it for your project too. In fact, you shouldn't need to. But I just put it up there. All right, why don't we calm down so we get started here. But I put it up here just to show you sort of the rate of innovation that's happening in this space. And pretty much, every week there's going to be new things like this being announced, new tools for people that are trying to use this set of data parallel programming environments to solve big problems. So this is just an example of that. There's a link on the bottom of the page. Yeah. Yeah, good. So the question is, when we're using Hadoop locally, we get to see, standard out and all these, get to see what's running where. Are we going to get to see that on EC2? And I think the answer is, we're trying.
So we've got a situation here where in order for all of us to share the same 30-grand account, we all have to run through kind of at one step removed. So we've got this big script base that allows you guys to pretend to be Professor Franklin. We're trying to set that up so you can also pretend to be Professor Franklin to see what that standard output stuff looks like. So that's definitely one of the reasons that part 1 is live right now and part 2 is not, is we're going to try and see if we can close that gap today, tomorrow, Wednesday, sometime before Sunday, so we can let you know how project 2 works so you can move on to doing stuff in the cloud while still receiving debug messages.
Right. So, if you were using EC2 directly with your own credit card and your own account, you'd see all that stuff. We just have a little magic we have to do so that you guys don't have to set up your own accounts with Amazon. You set them up with us instead. Okay? Oh, and we're going to have to get them. I don't have the forms, so we'll have to bring those in Wednesday. All right. So the topic for today is the second part of the data parallelism lecture. So remember last time we talked about 2 types of data parallelism? Oh, sorry. Before we even did that, we talked about request level parallelism, which is kind of the simplest thing you can do in a big system. It just says if you're doing a web search and I'm doing a web search, they don't relate to each other. We can just run those at the same time. Okay, that's request level. Data level parallelism, we talked about there being 2 types. At the disk and server level, so that's what we talked about last time, kind of coarse grain. That's what MapReduce lets you do. It lets you run, a single big kind of meta request like your web search over lots of data. Although you don't use it for web search, but like building the index, let's say, that supports your web search. So we talked about that last time. So what we're going to talk about today is the other type of data level parallelism, which is much smaller, much finer grained, and that's for data that's sitting in memory of a single machine. Okay? So that's what we're going to talk about today. Graphically, where does this fit in? Well, this is our warehouse scale computer. It's made up of a bunch of racks. Each rack has a bunch of servers in it. Each server has a bunch of cores. If you drill down on that core, you can see memory and instruction units and functional units like adders and so on. And then, of course, there's logic gates. Today, we're going to focus on this part. So within a single core, within a single processor, how do we get parallelism? How do we get data parallelism? Okay? So that's where we're at kind of graphically or pictorially. Okay, so how are we going to do it? Spend a little bit of time at the beginning talking about this taxonomy of different types of parallelism that goes back a few years. And then we're going to talk about a particular entry in that taxonomy called SIMD, Single Instruction, Multiple Data. And then we're going to talk about an implementation of a SIMD model, in particular an instruction set, which is an extension of the Intel x86 instruction set called SSE. And SSE is actually, I believe, the topic of your lab this week. So it's something you'll get to play with firsthand. Okay. So this is kind of straight out of the book. I don't want to spend too much time on this, but it's just basically saying when you're talking about parallelism, you've got sort of two general classes of things that can be parallel. You can have parallel software and you can have parallel hardware. Okay? And in software, typically you talk about things either being sequential or concurrent. Right? So concurrent means that multiple things can be logically happening at the same time. Right? They can be going on at the same time. In hardware, we typically talk about serial versus parallel. Okay? And again, parallel means you can really have things happening at the same time. So concurrent means they might be active in overlapping periods, but you don't necessarily have to have parallel hardware to run a concurrent program. So that's what this is trying to show. So if you're over here, sequential program on serial hardware, basically, it's just single line through the code, nothing happening that's very fancy. When you move over to running concurrent stuff on serial hardware, that's where, like the example given here is like a Windows operating system, where you have multiple processes, where maybe those processes are taking turns with a single core. So, at any given instance, that core is only running one of those processes. But if you step back, over a period of time, both, multiple processes are active during that period of time. So that's what we mean by concurrent. Okay, we're not going to spend too much time on that stuff. We're going to really focus on this next part, which is really the parallel hardware. And again, you can have sequential code running on parallel hardware. We'll actually show you what that looks like today. And then you can run concurrent code on parallel hardware as well. Okay? So just, you got to keep straight in your mind whether you're talking about, concurrent software, parallel hardware, or both. All right, so here's the famous Flynn taxonomy. I very cleverly color-coded the important leading initials here. So basically, what the Flynn taxonomy says is, moving to this world of parallel hardware, okay, you can have parallel hardware that basically runs multiple data streams at the same time. Okay, that's the D part. And you can have parallel hardware that runs multiple instruction streams at the same time. Okay, that's the I part. Okay, so just like when we did caching, at that level 1 cache, we split the cache into instructions and data, right? Because in some sense, they're both things that you're going to get from memory. Same thing here, right? We get instructions from memory, we get data from memory. We can get multiple instructions at the same time. Okay, that's going to be multiple instruction streams. Or we can get multiple data items at the same time. That's going to be multiple data streams. Okay? And the taxonomy just says, okay, I've got two options for the data, single or multiple. I've got two options for the instructions, single or multiple. So put them together, you get 4 options. That's the taxonomy. So if you look at each one of these, they have, we're going to focus on that one. I don't even know how to pronounce this one. SysD is basically no parallelism. I get one instruction running on one data item, okay, and then I either run that instruction on the next piece of data, or I get the next instruction, okay. So SysD is no parallelism, basically. This MISD we'll talk about in a second, but we're not going to say much about it. But that's you have a single item of data and you're applying multiple instructions to it. Nobody does that, so it's not all that interesting. It's plausible, but not that interesting. Where we're going to focus is on the multiple data stream side. And there you've got sort of two choices. SIMD, which is you bring in a bunch of items, a bunch of data items, and you apply a single instruction to all of those data items. That's SIMD. That's what we're going to talk about mostly today. And then MIMD, which is multiple instructions, multiple data. That's sort of the most flexible one, right? So I'll show you pictures of these in a second. So really, what you get today if you buy a processor or a machine, it's going to be, it's either going to be SIMD or MIMD, or actually probably some combination of those, okay? So everything's going to work on multiple data streams. Okay. There's also another taxonomy that we're not going to spend too much time talking about now. We might go back to it later in the semester. But there's, if you think about, this Flynn's taxonomy is about hardware. There's a similar one about software. And the thing that's probably most relevant on the software taxonomy is this thing called SPIMD, so single program, multiple data. So that was like the kind of thing that we were running, that we saw when we did large-scale data parallelism last class, where you had sort of a single program that was running, but it was running over lots of data. The different pieces of the program that were running on different servers might be executing different instructions at a given time, right? So SPIMD is something you might see in the literature or in your reading. That's why we put it here. But it's really about the software. And our focus today and for the next few classes is on the hardware. Okay? So we're really going to live in this SIMD, MIMD world. Okay, so the focus for today is SIMD, and sometimes it's called hardware-level data parallelism. And where SIMD comes from is really array processing. So a lot of the early uses for this type of processing were for doing linear algebra types of things, or for doing multimedia. And also, I guess, signal processing is up there, too. So I'll show you examples of all this, all right? But the key takeaway from this Flynn taxonomy, and I'm going to walk you through each of these boxes, is really just, you can have multiple data items at a time. You get hardware parallelism that way. You can have multiple instructions running at the same time. You can get hardware parallelism that way. And then you get these different combinations, okay? All right, so that's the famous Flynn taxonomy. And if you look up on Wikipedia, it tells you who Mr. Flynn is or was, and you can find out more. All right, so let's just look at each of those boxes. So the simplest one is SysD, so single instruction, single data. Basically what that means is no parallelism at all. So this is probably the way you thought computers worked before you showed up in 61C, right? It's kind of the simplest model of computation, right? So, you load an instruction that you want to run. That instruction needs some data, right, that's in a register, or first you bring that data into the register, and then that instruction processes that data. Okay, it's the simplest thing, and so a traditional uniprocessor machine is a SysD architecture. Okay, MISD, so this is, if you kind of try to decode this, so one item comes in from the data, and it gets put into both of these processing units, and then multiple instructions. One processing unit runs on this copy of the data, another instruction runs on this copy of the data. Okay, that's MISD. If you look around, I think even on Wikipedia, it talks about some machines back before any of us were born, which tells you how long ago it was, that might have worked this way, but you just don't see these in the wild anymore, so we're not going to spend too much time on that. Okay, so now we'll get into the interesting ones. SIMD is what we're going to focus on today, and it's basically a single instruction that gets applied to multiple pieces of data at the same time. Okay, so the way we're going to show that is we have multiple processing units. We get a single instruction that's going to run on all of these processing units, and then each one gets its own piece of data to run on. Okay? And that's how we're going to get parallelism in this scheme. Okay? And you use this kind of processing all the time. In particular, graphics processing units, GPUs, tend to use this type of parallelism. You get a bunch of data, and then you run, an instruction on it, and then you get a bunch more data, and then you run an instruction on all that data, and so on. Okay? And so this is going to work when you've got a big array of items, and you want to apply the same operation to all the items in that array. Okay? So this isn't how you're going to do, build your index for crawling the web. That's what we talked about last time in terms of MapReduce. This is for very, kind of specialized workloads where you're kind of chunking your way through big arrays or matrices of data, and you're applying the same transformations to everything in the array. Okay? Both of them are important. Both of them give you good speed-ups. They're just different ways of thinking about parallelism. But the key point of all this stuff, and the reason why parallelism has become elevated into one of the big ideas in this class now, is because that picture I showed you at the beginning of the class where we looked at everything from the warehouse scale computer down to the logic gates, the way you speed things up, when you run into a world where you can't use any more energy or you can't make the clocks on your processors go any faster because you're running into heat limits and things like that, the only way to make things go faster is to start doing more work at the same time. Okay, and so parallelism is a key technique across all those different levels of the system, because at some point you hit the limit of what you can do with any one item, and you have to start replicating them to go faster. Okay, so that's why it's important. So that's SIMD, and then MIMD, as I said, is sort of the most flexible. There we have multiple processing units. We can have these processing units doing this instruction. At the same time, we can have these processing units doing this other instruction. Okay, and then we're bringing data, into the, different data items into each of these processing units. And I think the way this is drawn is these two guys get the same data item, these two guys get the same, a different, but they get the same one. A different item goes to these two, and a different item goes to these two. And the instructions, these guys are running instruction 1, these guys are running instruction 2. Okay, so it's kind of, if you think about it, it's kind of the most you could have going on at the same time in hardware. Okay? And at the hardware, this is our view of the world on a single chip. But if you sort of squint your eyes and you think about that warehouse scale computer that we built, right, that had, a bunch of cores in a chip, right, a bunch of chips in a server, a bunch of servers in a rack, a bunch of racks in an array, it's doing the same thing too. Lots of different data items being operated on at the same time by lots of different instructions. So MIMD is sort of the way the world mostly works. Okay? And we'll talk about this. We'll talk about other forms of MIMD. We already talked about the coarse-grained MIMD in terms of MapReduce. We'll talk about more hardware-oriented versions of MIMD in the next few lectures when we start talking about thread-level parallelism and things like that. Okay, so that's Flynn's taxonomy. So, the easy thing there is you got two options in each dimension, right? The data dimension and the instruction dimension. 2 times 2 is 4. That gives you 4 possible architectures or classifications of architectures. One of them isn't parallel at all. One of them actually, for various reasons, doesn't really make much sense. The other 2 are very important, and those are the ones we're going to see all the time, the ones that let you operate on multiple data items at the same time. All right? Any questions about that? That's sort of the first big topic I wanted to get through today. Yeah. No, okay, good question. So the question is, the hardware deals with this, there's no software, and the answer is no, and we're going to see that. So yes, the hardware deals with this, but the software has to be written in a way that this works too. And so there's kind of 2 ways that happens. One is that the compiler does it for you automatically. That's kind of the nice way. The other way is the way you guys are going to do it in lab, which is you actually have to write your code a particular way to get this to work. Yeah?
So just to clarify, SIMD is sort of like a hardware way of doing mapping, like a mapper?
Okay, yep. That's a good way to think about it. That's a great way to think about it, actually. Thank you. The comment for you guys in the back couldn't hear it is, so SIMD is really just a hardware way of doing a map, a map from MapReduce. And that's absolutely true. Each one of these is a single data item that this instruction gets applied to. So in some sense, you're applying that instruction, you're mapping that to every data item. That's a good way to think about it. But the key thing that you said is this is happening in hardware. So that's the big difference. Did you have a... Uh-huh.
Ignoring Amdahl's law, just in terms of what comes with my computer, how much of the software that I can buy would even be able to do?
Okay. Whew. Okay, good question. Okay, so that question was, if I went out and bought a 12-core processor today, how much software that's out there is able to use it? And so a couple things I want to say. First of all, first of all, I hit the wrong button. This actually works on a single core, so this isn't all about multi-core, okay? And I'll show you how this works in a second. But I think the answer to how much software out there today can use multiple cores, so certainly things like operating systems, where you have lots of different types of tasks happening, those can very easily use multiple cores. Right, because you have a process over here that's running your email. You have another process over here that's doing your compilation. You have another process over here, that's checking your tweet, your Twitter feed or something. Those are all independent. Those can run on different cores. When you start actually looking at software, individual programs that could use multiple cores, then it gets a little trickier. Again, it depends on if it's a big program that's doing a bunch of different things with different processes and it works. If it's something like, just say like running a compiler or something, actually most of them don't use multiple cores very well. So, but that's going to change. That's going to change over time. Yeah.
Are the examples of like a single data stream?
I'm going to show you. So we'll make this more specific. Okay. Yeah.
So when you have multiple cores and stuff, will each process still be able to do stuff like the serial stuff where you do multiple programs?
Yeah, okay, right. So let me make sure I got your question right. I think the question was, even if I have multiple cores, can't those multiple cores be doing this kind of stuff? Can't they be doing SIMD stuff? And the answer is absolutely. So you're going to have sort of parallel, you're going to have many cores running in parallel, and each of those cores is going to have a bunch of stuff internally running in parallel as well. And each of those things is going to be having a bunch of logic that's running in parallel, but hopefully I'll get Dan to tell you about that. Okay? So yeah, it's parallel. That's what that first picture was trying to show you, was it's parallel all the way from, the biggest warehouse scale computer you can build all the way down to the individual, gates and logic of a single processor. Okay, and all those things are running in parallel stuff. Okay, good. All right, so let's drill down now on this one particular type of hardware parallelism called SIMD, which again is single instruction, multiple data. Okay, so here's an example where you might want to do that. So let's say we wanted to have a coefficient vector that we're multiplying a data vector by. Okay, so here we've got some. We've got an array that we're going to index by I, and for every I, we're going to multiply the I value from this data array X times the coefficient at I, and we're going to store that in y sub I. So basically, if you have, if I goes from 0 to n, you basically, or n minus 1, you basically have n independent multiplications you can do here, right? Because the result that I get for y sub 1 is totally independent of the result I get for y sub 2. So if I could get my hands on x sub 1 and c sub 1 in one processor, and I can get my hands on x sub 2 and c sub 2 in a different processor, I can run those at the same time, and it'll just go twice as fast. Okay? Barring Amdahl's law, which we'll talk a little bit about later. Okay? So that's the whole idea of SIMD, right? That you have the same operation you want to do over and over again to different pieces of data, maybe what you want to do is bring all that data in, bring multiple pieces of data in at the same time and apply that instruction to them all at once. Okay? So why is this a good thing to do? Well, we haven't talked about this too much. We're going to talk about it in a few more lectures. But remember, the instructions are sitting there in memory. Okay? So when you increment the program counter, that says, hey, get the next instruction. You have to bring that instruction in from memory, and then you have to, so that's called a fetch, right? So you fetch the instruction. Then you have to figure out what the instruction is. And remember, even in MIPS, which is a pretty simple machine language, right, you have to understand, which of my, 3 formats is this, and once I figure out which one of those, and I got to pick apart, okay, which is the opcode, which is the operator, and so on, okay, the operand. So there's a bunch of work you have to do to actually figure out what the instruction is. So what's nice about SIMD is you bring that instruction in once, and you fetch it and decode it once, and then you apply it to a bunch of data. Okay? So you kind of amortize, you pay for that fetch and decode cost. Instead of just for every data item, you can spread the cost of that out across multiple data items. Okay, so that's one big savings, is the fetch and decode cost. The other thing is that if the operations, if the data is small relative to, say, a cache block, all right, or relative to, say, the number of bits you have in your memory bus, well then, in one operation, you could bring in multiple data items, okay, for the same cost as bringing in one. So again, you're going to be able to get that savings as well, all right? So that's what this idea of pipelining and concurrency means. You can bring in multiple things at the same time, often for the same cost, or just a little bit more than bringing in one thing. So you're going to get a savings that way. Okay, so again, it's just this kind of economic argument that, if I have a big upfront cost, I have to pay for something. If I can spread that across multiple operations instead of just one operation, the relative cost of that overhead is going to go down. And that's going to make things run faster. Yeah? Okay, I'll show you how this works on a single core. But yeah, this is all going to happen on a single core. I'll show you in a second. All right, any other questions about that? Okay. All right, well, how does that work? Here's the answer to your question in a picture form. So the particular version of SIMD processor that we're going to look at in this class is the one that was developed by Intel. And you may have heard of the MMX extension to the Pentium, I guess it was Pentium 2, the Pentium 2 instruction set. So it was proposed as a multimedia extension, right, which was supposed to improve graphics. It was a graphics accelerator. But you'll see that what's happening is, what it really is a SIMD processor. And eventually, so MMX was put into the Pentium 2. It was replaced in later versions of the Intel processor with this thing called SSE, the Streaming SIMD extension. And that's what we're going to talk about today, is this Intel SSE thing. And that's what you're going to play with in your lab this week. All right? But SSE was Pentium 3 and beyond. And then, as we already talked a little bit about, what's really happening in a lot of systems now is this whole set of functionalities moving over to the GPU. Okay, so for graphics processing, you've got a completely separate processor that's sitting next to your regular processor that's doing the graphics. Okay, and it's going to make very heavy use of this single instruction, multiple data approach. But what an interesting thing that happened is that in the meantime, these instructions ended up becoming the preferred way of doing a lot of floating point operations in regular processors. So that's why the instruction sets are still around, even if a lot of the graphics processing is moved off board, right? So, and you'll see why in a second. But now, if you take the lecture Dan did on floating point, and you extend that so that instead of just looking at one floating point word, okay, you can look at multiple words. So let's say we had 4 floating point numbers here, and we had another 4 floating point numbers here. So think about that example where we were multiplying one array times another array, okay? Well, so if you have the 2 arrays here, here's 4 items of the first array, here's 4 items of the second array, you can apply that multiplication in parallel to each of those pairs, and you get 4 answers, okay? So in the amount of time, the amount of clocks that it would take in a normal processor to get one answer, here you can get 4 answers. Okay? Subject to the fact, if you're doing a good job with your cache, that you can actually bring all 4 of those in and all 4 of those in, either at the same time or for cheaply. Okay? So to get to the question that was asked earlier, this is what's happening on a single processor. There's instructions that basically let you read 4 things at a time and operate on 4 things at a time. And it's all happening within a single processor. Okay? I think another question back there first. Yeah?
That was like in a for loop that function we showed before. What if there was like an X with the I minus 1? How does it know, oh, it doesn't depend on a previous value that has to be like that?
Yeah, okay, so good question. So how does the compiler know, or how does the system know that it can play this trick? I'm going to show you either at the end of today or the beginning of Wednesday, basically some special code that you write that you tell the compiler that it's okay. But you can imagine, and there are systems that do this, smart compilers that analyze the code and figure out that this kind of stuff would work. Okay, and I'll show you a trick probably on Wednesday called loop unrolling that does that. It's very simple compiler optimization. Is there another question down here? Or you're all set? Okay. Yo. Yeah, okay, so the question was, isn't it possible, so for this compilation trick where the compiler figures out what steps depend on each other and which ones don't, isn't it sometimes possible to translate a statement statements that look like they depend on each other into statements that are independent? And the answer is absolutely, for some limited cases, that's true. And smart, that's what often, it's tricks like that separate a really good compiler from a not as good compiler, right? It's how smart the compiler is at saying, hey, this looks like these things depend on each other, but if I rewrite it this way, they don't depend on each other anymore. And again, I'll show you a simple version of that with loop unrolling next time. Yeah, in the back.
Why don't data centers use GPUs for the majority of their computations?
Oh, okay. Well, that is a great question. So why don't data centers use GPUs for the majority of their computation? And the answer is there's a lot of people asking that question right now, and so more and more data centers are starting to use the GPUs more for certain computation. And I'm sure you don't remember, but if you look back in the notes, I showed you a bunch of different offerings that EC2 gives you if you want to buy a machine, if you want to rent a machine, there's different kinds of machines you can rent. And one of them has extra GPU support, and use it for stuff like that. Yeah?
So here it looks like you have the ability to do 4 things at once. Is that number 4 like just an upper bound based on your hardware? Can you like make it higher than that using some like software stuff?
Okay, so the question is, here we're showing 4. Is that an upper bound on the hardware, or can you do better than that using software? This is all the tricks we're playing here are happening at the hardware level. So this is kind of as fast as you can go. If you've got a hardware system, and I'll show you, I think, on the next slide what this looks like, that's doing 4 at a time, that's kind of what you're stuck with at the hardware level. Okay? All right. One more, and then I want to keep moving. Yeah? Yep. That's a good question. So what if I don't need to use all 4? What do I do then? And the answer is, that's a good question. I think this is probably slower. If you were always doing this with one word, it would probably be slower than just doing the normal thing with one word. Okay? But the idea here is that most of the times you're really filling this thing up with 4. Okay? Okay, one more.
What if it's not just one instruction? Say I want to multiply and then add a constant.
Oh, jeez. Okay. So what if it's not just one instruction? What if I want to multiply and add, say? Okay, so it depends now on which part of the religious divide you're on. Okay, so we haven't talked about this yet, but the MIPS machine that we study is what's called a RISC system, which is a reduced instruction set system. And the reduced instruction set answer to that is, okay, well, that's why we give you the ability to run multiple instructions, right? You figure that out. The CISC which I don't know if does the C stand for complex. I've been so brainwashed by the RISC people because Berkeley is just full of them. I don't even remember what CISC stands for. But the x86 is a CISC system. It's the opposite of RISC. It's not a reduced system. They actually have instructions that do exactly. They have a single instruction that does multiply and add, for example. I'll show it to you. Okay, so let's keep going. So here's our language. So here's what we're going to do. We're going to, for each f in some array, we're going to take its square root and store that. Okay, now if you were going to run that in SysD mode, right, non-parallel mode, that ends up looking like this. So you put f for each f in the array, you put f in the floating point register, you calculate the square root, and then you write the register out. Okay? And you do that, so how many times does that run? Well, it's the size of the array. Number of elements in the array, that's how many times you run those instructions. So load, square root, store. Okay? If you want to do it SIMD way, well here, what we do here is we change that loop ever so slightly to go through the array 4 at a time. Okay, and then what we do is we load 4 things. I mean, this sounds so simple, but you got to actually implement this in Silicon. It's a little complicated. But you read 4 things at once, then you calculate the square root for each of those 4 things, and then you write those 4 things back out. Okay? So if you're just counting instructions, this is 3 instructions times the number of elements in the array. This is 3 instructions times the number of elements in the array divided by 4. Okay, so ignoring sequential parts of that processing, you're basically going to run 25. It's going to run, in 25% of the amount of time it took you the old way. Okay, and if you're sitting there playing Doom or whatever you guys play these days, that matters, right? Because that's the difference between getting killed and not getting killed. So, that's why this stuff matters. Okay, so it's those kind of delays. Yeah.
So if you use a smart compiler that knows that you can do parallelism and will try and do this type of stuff, then do you have to compile it differently for machines with different amount of cores?
You do. So with all this stuff, I'm sorry. Okay. Okay, sorry. I'm sorry, what was your question again?
So if you have a smart compiler that knows how to use multiple cores,
Yeah.
would you have to compile differently for computers with different amounts of cores?
Okay, so the question was, if I have a compiler that's smart enough to compile for different amounts of cores, do I need to recompile for a different machine? First, before I answer that question, I want to point out this isn't about cores. This is all happening in a single core. Okay, so I have one core that's able to run instructions that process things 4 at a time. Okay, now the basic answer to your question is yes. If I'm moving code from one architecture that supports this kind of stuff to another architecture that doesn't, I'll probably have to recompile it. Yeah. Yeah.
Do you have to recompile it anyway? Whether or not they
It depends on, so the question is when you have to recompile it anyway. I mean, it really depends on how compatible the underlying architectures are. So you can run on multiple versions of Intel chips and you don't have to recompile.
Is it possible that there are the same architecture but different parallel?
Yes, so if you look at sort of the Intel Pentium family, there's actually programs that you can run that'll tell you what processor you have, because they have different capabilities. Yeah. Oh boy. Okay. I do want to get through this lecture. Yeah. Okay, if you can do this, why would you ever not do this? Because there are going to be some cases that don't fit so nicely into this kind of framework. So this is great for going through arrays and taking a screen and applying a transformation to everything on the screen. It's really bad for doing database queries. Right? There's no real good way to use this for doing a single lookup of something. So it depends on the workload. But bottom line is, if you can do this sort of thing, yeah, you should probably do it. It's faster. Okay, one more. Oh boy, how does parallelism work for interpreted languages rather than parallel languages? Can I not answer? Let's take that one offline. I get one question a class where I get to say, let's take it offline. So that's my one for this class. All right. Okay, cool. So let's keep going. All right. So this is actually kind of a weird thing that was in the book, but this is the original MMX system, what it supported. So it supported different kinds of add and subtract. max, min, minimum. So here's where we get away from the RISC thing. You can actually give it, 4 16-bit integers, and it'll tell you which is the smallest, right? That's not really a RISC instruction. Average, that's not a RISC instruction, really, and shift and rights, which are. But the bottom line, you get these different instructions, and you can apply them to different chunks of data. So you could say, hey, I've got 8-bit characters, or you could say, hey, I've got 4 16-bit words. Okay, so in Intel speak, a word is typically 16 bits. In MIPS, we've been talking about a word being 32, so you got to kind of keep track of that. But this was the original MMX that was done, like I said, for graphics processing. The one we're studying is this SSE, the streaming SysD extension, and that supports bigger operands. So 16 8-bits or 8 16 bits. So what's that, 128 bits. So what does that look like? Well, it kind of looks like this. I can either say I've got a bunch of bytes. I can say I've got a bunch of 2-byte words. I have half as many double words, or I have half as many quad words. Okay, so in Intel speak, a quad word is 64 bits, right? Because the individual word is 16. So if you're doing single precision floating point, the kind that we learned mostly, in the floating point lecture, that's going to work on double words. That's going to be here. So you can have what? 4 single precision floating point numbers in a single operand. Okay? If you want double precision, right, you need more decimals to the more places to the right of the decimal. Then you need more bits, so then you can only have 2 of them. All right, so that's for double precision. Okay? I'm going to have to keep moving. Okay, so what did they do? Well, in order to make this happen, the Intel architecture added a bunch of new registers. So they have these XMM registers, 0 through 8, which are 128-bit data registers. Okay? So those got added to the architecture in addition to these new instructions. So what did we add? We added instructions that are capable of operating on 128 bits at a time, right? Split up either as 4 floating points or however many characters that is, right? And then we had to add registers that were that big too. Okay, so that's what these special registers are, XMM. Okay, and then this is a bit of an eye chart. You can look at it later. But basically you've got move operators, you've got arithmetic operators, you've got comparisons, and all the comparisons you decorate them with these little abbreviations. So PS means packed single precision. So that means that operand, that 128-bit operand, is going to be 4 32-bit floating points. Okay? If I say PD, then that's packed double precision. That means it's going to be 2 64-bit floating point numbers. Okay? So when I say, add immediate, I have to say, am I doing that with a, packed single precision or packed double precision, right? Because that's going to tell me, am I doing it am I doing those adds on 2 64-bit floating points, or am I doing it on 4 32-bit floating points? Okay? So that's what these things are. This is kind of interesting too. This is another place where we get away from the simplicity of the MIPS model, where if you decorate it with an A, it says, hey, you got to get this 128-bit chunk from memory, and it's aligned on a 128-bit boundary. That's what A means. U means it's not aligned, unaligned. Okay? So whereas in MIPS, it would say, hey, you're out of luck if it's unaligned. You're going to get the wrong thing. Here, you can get the answer. It's just going to be slower. It's going to be a little slower to get that unaligned one than the aligned one. That's, again, the distinction between this RISC approach, which is keep the processor and the instruction set as simple as possible, and the CISC approach, which says, hey, make the language higher level so that it's easier to program, for some definition of easier. Okay, and then there's some other stuff here. So you've got all those instructions, movement instructions, different adds and multiplies, sort, max, min, and then comparisons, different types of comparisons. Oh, okay, sorry. So Professor Garcia was confused about something, so let me unconfuse him. So when we say add, it's like the picture I showed you. You're not adding up those 4 things in that XMM. You're adding 2 XMMs, right? So just in case, I know he wasn't confused. He was just trying to help you guys out. Okay? So that's why if you read this, it takes one of these big registers and either a memory location or a big register. Okay? And it adds them together. Okay? Okay, so let's look at some example here. I've got this vector I want to add, I've got two vectors. I want to add the two x's together, the two y's together, the two z's together, the two w's together. So the way that looks in this SSE instruction sequence, so I'm going to move, let me decode this. So I'm going to move 128 bits from memory into the XMM register. Okay, the A tells me that it's aligned. The PS tells me that when I look in there, I'm going to find 4 32-bit floating point numbers. Okay, and in fact, you don't know that, but it's going to be X, Y, Z, and W for V1. Okay? All right, so that's what that first instruction does. Then the second instruction says, I'm going to add, again, packed single precision, whatever's in XMM0 to whatever's at the address of V2. So remember, I'm adding V1 and V2. All right, so that's going to do those 4 adds in parallel. And the result goes into the XMM0 register. Okay, so at the end of this instruction, I've got a 128-bit register. I'm referencing a 128-bit chunk of memory, and I'm saying treat each of those 128 bits as if they were 4 32-bit floating points, and then add each of those pairs together and put the result in my register. Okay, that's what that does. And then if I want to output it, then that's a move where basically I'm moving from that register to the address where I want the result to be. Okay, so it's 3 instructions, and I just did 4 floating point adds. Yeah, if you got something quick.
Why do we have to specify that it's a back single for the movement step?
Okay, so the question is, why do I have to specify that it's packed single precision for the move instruction, given that I'm just copying the bits? That's a really good question. I don't actually know the answer to that. So, okay, I will try to find that out for you. All right, so, where does this show up in real life? Well, like I said, the first part of this was, originally this was done for graphics processing. So why? Well, how do I represent my screen, right? So here's my screen, right, where I'm playing Doom or whatever. I've got a chunk of memory called the frame buffer. And the frame buffer isn't just, we talk about pixels as being on or off, but as you guys know, pixels have a lot more information, right? It's the color, the intensity, and all this stuff. So the frame buffer is actually a deep, a pretty deep structure that basically has a bunch of slices that are the size of the screen. Okay? So what this example is showing here is that pixel 0 is represented by this array. Pixel 1 is represented by this array. And if you look at the bits, you can see that pixel 0 is lighter than pixel x. Okay? But basically, these are just numbers that are sitting in arrays that you want to do processing to. So for example, you might want to convert an image from one format to another. So say from a bitmap image to a color space image, YUV image. Okay? So what you do is you can take each of those 8-bit monochrome pixels, and you can basically pack those into a 128-bit register, right? So you get 16 pixels in your 128-bit register. Now you can process 16 of those at a time. Okay, that was really the motivation for this stuff. Okay, so this gets to the question then about what if I need to do more than one operation? And the answer in the Intel SSE instruction set is we've got an instruction for that. Okay, you want to do it? We've got an instruction for it. So this one is floating point multiply and add packed single precision. Okay, so basically, if you look at what you're doing, there's typical types of transformations where you've got 2 floating points. You want to multiply them and you want to sum up the results. Okay, that's what this FM add PS instruction does. Okay, so let me just show you what it looks like quickly. This is what it looks like in C if you were to do it. Wait a minute. If you were to do this in individual x86 floating point instructions for four floating point numbers, you'd have to do 8 instructions, right? You do the multiplication, then you do the add, right? And you do that 8 times. If you were to do it in SIMD style, but you didn't have that fancy multiply and add instruction, then you could do them 4 at a time, but you have to run 2 instructions on each one. So that's 2 SSE2 instructions. And if you have this special instruction that basically lets you take things 4 at a time, do the multiply and then add up the answer of all 4, then you can actually do this whole thing in 1 instruction. So you go down from doing 1 instruction. You used to do 8 instructions before you had this SSE extension. Now you only do 1 instruction. Okay, that's the power of this. Okay, so let me just wrap up. So I talked about this taxonomy of hardware parallelism based on instruction parallelism and data parallelism. And then we focused on this one implementation of a SIMD architecture, the Intel extensions for stream SIMD processing. What we're going to do on Wednesday is show you what those look like in a C program. And that's what you're going to be doing in your lab. And then we're going to move on to other parallelism stuff. Concurrent software on serial computers just means that you've got a bunch of,